Chapter 3 in our textbook is called Composition of Substances and Solutions. We're going to learn about what a mole is and something called Avogadro's number. This will allow us to interconvert between our laboratory scale of grams and that small submicroscopic scale that we can't see of ions, particles, atoms, etc. Later at the end of the chapter, we'll learn about what a solution is composed of and how to calculate molarities of different solutions. If you remember back to chapter 1, when we learned about the fundamental units, the unit in chemistry for amount of substance is the mole. The abbreviation is MOL. The mole is essentially a convenient counting term which allows us to interconvert between masses that we weigh out in the lab in units of grams, and eventually we can figure out how many particle units are in those grams by simply weighing them. So if we're talking about a pure element, maybe carbon, we can figure out how many small atoms of carbon are contained within a sample by taking a mass of it on a balance. The mole allows us to do this. An analogy to this is, imagine if you had to do a project and you needed a large amount of nails. If you went into a hardware store, you wouldn't simply count out 1,000 nails. That would be a lot of work. Just like we can't go into the lab and count out 1,000 atoms of carbon. But we can take a mass and figure out how much we need to weigh out to get 1,000 atoms. Just like we could take a mass of a certain number of nails and determine how much we need to weigh that would equal 1,000 nails. And we could figure out, based upon if 3 nails we were told weighed 0.15 pounds and we knew that 1 pound costed $2, we could use those unit conversions to essentially figure out our cost for 1,000 nails. This is going to be the same idea that we'll use when looking at moles and grams and number of atoms. Let's define what a mole is. 1 mole is specifically defined as being the number of atoms contained within 12 grams of the isotope carbon-12. If you recall from the last chapter, that's exactly the same way that the AMU, or atomic mass unit, was defined. 1 AMU was 1/12 of the mass of 1 carbon-12 atom. So if we were to multiply that by 12, the mass of 1 carbon-12 atom would be exactly 12 AMU. This means that any atomic mass that we read off the periodic table is going to be equal to 1 mole of atoms for any given element. So that decimal number at the bottom of the tile, or the average atomic mass, will be called our molar mass, and it will be equal to the mass in grams of 1 mole of a given element. So 1 mole of any element that we look at on the periodic table is equal to the atomic mass of it in grams. So if we were to examine 1 mole of various elements, we could see that they don't all look like the exact same amount, but they are all 1 mole. That's because they all have different atomic masses, according to the periodic table. So 1 mole of carbon is 12.01 grams. 1 mole of hydrogen gas would be 1.008 grams. 1 mole of sulfur is about 32.06 grams, and 1 mole of zinc is 65.38 grams. We can look at any of these other examples and see that the molar mass will change depending upon what the element is. The molar mass of a substance is used as a conversion factor which allows us to convert between grams and moles. So for example, we saw in the previous slide that 1 mole of carbon was equal to 12.01 grams. We can use this as a fraction and say that 1 mole of carbon over 12.01 grams is the molar mass, or we can write it as 12.01 grams over 1 mole of carbon. So let's practice converting between moles and grams of an element. Determine the number of moles in 12.25 grams of argon. And argon is one of our noble gases, and it's an element. So we're going to start with what we're given in the problem, 12.25 grams of argon. And we're going to want to use the molar mass for argon to convert. Grams are going to have to go in the denominator, moles in the numerator, and that molar mass we're going to have to read off the periodic table. 1 mole of argon is equal to the average atomic mass in units of grams, 39.95 grams. So when we plug this into our factor label, we're going to want to put 1 with the unit mole, and the mass is always associated with the grams, 39.95 grams. We want to make sure our grams of argon cancel, and we're left in units of moles. And we should get 0.307 moles of argon. Now let's go backwards. Determine the mass in grams of 2.75 moles of calcium. So we're starting with 2.75 moles of calcium. And we're going to want to convert using the molar mass because that's how we get between grams and moles. And if we look at the periodic table, 1 mole of calcium is equal to 40.1 grams. So this time we're going to have to put units of moles in the denominator and units of grams in the numerator. And according to the periodic table, 1 mole is 40.1 grams. Our moles will cancel in this example, and we'll be left in units of grams, which should be about 110.3 grams of calcium. How many moles is 10.5 grams of lead? Looking at the periodic table, 1 mole of lead is equal to 207.2 grams of lead. So if we start with our 10.5 grams of lead, we're going to convert using our molar mass. Grams will go in the denominator this time, moles in the numerator, and 1 mole is equal to 207.2 grams. Our grams of lead cancel and left in units of moles. We should get 0.051 moles of lead for our final answer. Next, we're going to talk about something called Avogadro's number. We said that the mole was defined as the number of atoms in exactly 12 grams of carbon-12, but we haven't said how many atoms really are present in those 12 grams. We can imagine that atoms are very, very small, so there's going to be a whole lot of them if we have 12 grams of carbon-12. There is exactly 6.022 times 10 to the 23rd atoms in 1 mole of carbon. This is called Avogadro's number, named after the Italian scientist, and it specifies exactly how many particle units are in 1 mole of any substance. The particle units can change that are associated with the number. So the things could be the number of atoms, ions, molecules, if it's an ionic compound, formula units, pizzas, donuts, etc. Anytime you have 1 mole of a substance, you always have Avogadro's number of things within that mole. Avogadro's number is often abbreviated with the symbol capital N sub A. And I wrote it as 6.022 times 10 to the 23rd things per mole. But often when you see it written in a textbook, it won't have units of things associated with it. It'll be written as 6.022 times 10 to the 23rd per mole. That's because our things could change. So 1 mole of donuts is Avogadro's number of donuts. 1 mole of the element sodium is Avogadro's number of sodium atoms. 1 mole of silver is Avogadro's number of silver atoms. And when we use Avogadro's number, we're going to use it much like a molar mass. it's going to be used as a conversion factor. But this time, we're going to be converting between atoms or particles and the number of moles in a substance. So we can have 6.022 times 10 to the 23rd atoms per mole, or we could write this as 1 mole is Avogadro's number of atoms. And this is specifically when we're dealing with an element that we'll be talking about atoms as the smallest particle. So let's try an example, converting between moles and particle units. How many atoms, which atom would be our particle unit in this example, are there in 3.4 moles of gold? In order to convert between atoms and moles, we're going to have to use Avogadro's number. N sub A is equal to 6.022 times 10 to the 23rd things per mole. Our things in this example are atoms. So we're going to have to start with what we're given, which is 3.4 moles of gold. And to convert, we're going to have to put moles in the denominator and units of atoms in the numerator. We're going to want our moles to cancel and our atoms to be our final unit. We know that Avogadro's number says 1 mole of any substance is 6.022 times 10 to the 23rd things, in this case atoms. So our moles will cancel. We'll be left in units of atoms. And when we multiply, we should get a really large number because there's going to be a lot of atoms in a sample. And we'll get 2.05 times 10 to the 24th gold atoms. Let's try another example. How many moles is 4.5 times 10 to the 22nd atoms of magnesium? This time we're starting with units of atoms and we're trying to determine the number of moles, but we're still working between particle units, which is our atoms, and moles right now. We're going to have to use Avogadro's number. We're going to start with 4.5 times 10 to the 22nd atoms. And when we convert this time, atoms will have to go in the denominator, mole will have to go in the numerator, and according to Avogadro's number, 1 mole is 6.022 times 10 to the 23rd atoms. Our atoms will cancel and we'll be left in units of moles. And we should get 0.075 mole of magnesium. So remember that mole is just a convenient counting factor that lies halfway between our laboratory scale of grams and between the really small scale of atoms or molecules or ions or formula units that we can't see, those subatomic particles. Next, we're going to combine the concept of molar mass with Avogadro's number. This will allow us to convert grams of a substance that we could weigh out into moles, which is our convenient counting unit, then into our small particle units. The link between grams of a substance and moles is always going to be the molar mass, and we'll have to either calculate that or determine it from the periodic table. And the link between moles of a substance and particle units will be Avogadro's number, N sub A. So in order to convert all the way from grams into particle units, we always have to stop at Moletown in the middle. How many grams of carbon are in a sample containing 1.2 times 10 to the 25th atoms of carbon? So we're trying to find grams, and we know a number of atoms. So our strategy here should be to start with atoms And we're going to have to convert our atoms into number of moles. And then from moles, we can go to the grams of carbon. Our link to convert atoms to moles, or our particle unit to moles, is going to be Avogadro's number. And our link to convert moles into grams is going to be the molar mass, and of this case, the molar mass of carbon. So let's start. We have 1.2 times 10 to the 25th atoms of carbon. And next we're going to use Avogadro's number. Atoms are going to have to go in the denominator, so they cancel. Moles are going to have to go in the numerator. 1 mole is Avogadro's number, 6.022 times 10 to the 23rd atoms of carbon. We can see our atoms would cancel. If we were to stop right here and calculate, we'd be in moles. But we don't want to just stop in units of moles, we want to go all the way to grams. So we're going to have to look at the molar mass of carbon from the periodic table. The molar mass of carbon is equal to 12.01 grams per mole. And we can read that right off of the average atomic mass at the bottom of the element tile. So 1 mole will go in the denominator, and 12.01 grams of carbon will go in the numerator. Our moles will cancel, and we'll be left in units of grams. So our final answer should be 240 grams. Let's try another example. How many atoms of iron are in 54.3 grams of iron? So now we're going to work the other way around. We're starting with a mass, so we're starting with grams, and we want to take our grams and convert them to particle units of atoms. But first we have to stop in units of moles because that's our middle ground, and then from moles we can go to units of atoms. To convert between grams and moles, we'll need the molar mass for our substance, which is iron in this example. And then to go from moles to atoms, we'll need to use Avogadro's number. Here we have 54.3 grams of iron to start with. If we look at the periodic table for iron, we can see that the molar mass of iron, or 1 mole of iron, is 55.85 grams in 1 mole. Right now, our grams of iron would cancel and be left in units of moles. Next, we're going to use Avogadro's number to convert moles into atoms. 1 mole of iron is going to be equal to 6.022 times 10 to the 23rd atoms. So lastly, our units of moles will cancel, and we can calculate our number of atoms of iron in that sample. And we should get 5.85 times 10 to the 23rd atoms of iron.